Alright, so in this video, I'm going to go over discussion quiz number 3. So here we have the quiz. Alright, so question 1 tells us 4 charges are placed at the corners of a square. What is the direction of the net electric field at the center of the square? So first we'll go ahead and we'll draw our square. And we'll place our 4 charges at each of the 4 corners. And we know that the electric field is directed away from a positive charge, and these are all positive charges. So by symmetry, I see that the net electric field will add up to 0 because it's the same distance away from each of the 4 charges, and they're directed towards the center. So when I add them up, I will get no electric field. All right, my second question here says that a positive charge might be placed at one of 2 different locations in a region where there is a uniform electric field, as shown to the right. How do the electric forces on the charge at positions 1 and 2 compare? Now the key here is 1, that we are in a uniform electric field. That means the electric field has the same magnitude and same direction everywhere in space. The second part is that we have a positive charge and it's the same charge. Remember, if we had 2 charges of different magnitudes, whether positive or negative, then there would be different answers here at positions 1 and positions 2. But since we're placing the same charge and it's in a uniform electric field, the force at both positions is the same but not 0. All right, next we have the questions on Gauss's law. Now when figuring out these questions, we're going to want to make sure that we draw pictures, that we think carefully about the information given to us. Now the first question here, question 3, is a relatively straightforward application of Gauss's law. Remember, Gauss's law tells us that the net electric flux is equal to the charge enclosed divided by epsilon naught. Now in question 3, the key here is that we have a proton and an electron. And so when we add up the net charge enclosed, we're going to get 0. And that means that the net electric flux passing through the entire cube is going to be 0. Now it wouldn't matter whether we had a cube, a sphere, or a blob. The key with this question was looking at the net Q enclosed. So for question 4, we're going to place a proton inside of a cube of side A. So let's draw that up over here. And we're going to place that charge right at the center. Now we know that the net electric flux is equal to E over epsilon naught, because the net charge enclosed is 1 proton. But we're not asked for the total electric flux. We're asked of the flux through one face. Now, by symmetry, none of these faces is special, right? They're the same distance away, the charge is at the center of the cube. And so we'd expect that each one of them would have the same amount of flux passing through it. So all we have to do here is count up the number of faces and then divide 1 by it. So a cube has 6 faces, so the amount of flux to pass through one face would be 1/6 of the total flux. So answer choice D. Now questions 5 and 6 are much trickier than the first 2, but if you have a firm understanding of Gauss's law, these should be a piece of cake. Now, instead of having the charge at the center, we have the charge located at the corner of the cube. So we have the charge located right here on the corner. Now, the easier question, question 5, is asking for the flux through the faces that make up the corner. Now, these faces that make up the corner, let's pick the top one, for example. The area vector for the top face points up. And we know that the electric field for this positive proton is going to point radially outwards. So the electric field along the top face is pointed sort of to the left, and back and to the left, and then just straight back. But the key here is that everywhere on that surface, the area of the top is perpendicular to the electric field on the top. And we know that when the area vector and the electric field vector are perpendicular to each other, that even if there's an electric field there, the flux is going to be 0. And so the net flux through any of these three faces, the top, the front, or the right side, will give us 0. Now, there's a couple different ways to answer question 6. I'm going to try to approach it in what I hope is a more straightforward fashion. Now, one way we can think of this cube is, well, how can we relate it to the situation where we had the proton at the center of one cube? Now, if I imagine this cube as being part of a collection of a bigger cube that does enclose the entire charge, I might say that the Q enclosed is 1/8 of the total charge. To fully enclose this cube, I would need to add in 3 more cubes at the bottom, 4 more at top for 8 total. So instead of E being the charge enclosed, now we have 1/8. Now, if we use our answer from question 5, we see that none of the flux passes through the top, front, or right side face. So that all of the flux that will satisfy a Q enclosed of 1/8 E must pass through the bottom, the back left, and the back face. In other words, there are 3 faces for which the flux to flow through. So if I take 1/8 E over epsilon naught times 1/3, I'll get 1/24 E over epsilon naught. So my answer choice there is D. Now, I want to again point out how none of the answer choices relied on the shape, on the size of the cube, right? A didn't appear in any of these answers, right? And so that's an important aspect of Gauss's law.